For this example, when r is given -4 tangent theta, secant theta, they want you to jump from polar to Cartesian. Polar to Cartesian. And I gave you formulas how to do that. Solution. None of these formulas work. Because what the heck, we have tangent and secant. Formulas work with sine and cosine, r squared plus y, r squared equals sine squared plus cosine squared, that kind of stuff. X squared plus y squared. So my first recommendation, when you see weird functions, tangent, secant, cosecant, cotangent, write down the definitions. Sometimes they just cancel out. Maybe we're overthinking. R equals -4. Tangent is sine over cosine. Secant is 1 over either sine or cosine. Which one?
Sine.
So it's always the other way. If it starts with S, it becomes C. Took me years to memorize that. But finally, some student told me, remember, it's always the first letter. If it's S, it will be C. If it's C, it will be S. Genius. Since then, I was always safe. Because again, reminding you, in Europe and other countries, most of us don't have secant and cosecant. You guys created it for some reason. So many of us are surprised even seeing them. 1 over cosine. Look at this cute square. That's interesting. So it did not cancel out. Kind of made it worse, but whatever. It is what it is. Recently, I'm saying it too often. Sine theta, cosine squared theta. This is what we have. Okay, so now at least we have sines and cosines. Let's get rid of the denominator. In general, if you see a fraction in polar, there's a hint that it's not correct. So maybe let's get rid of the fraction by multiplying both sides by the cosine squared. It becomes r cosine squared theta equals -4 sine theta. Okay, very interesting. If you see 4 sine or 4 cosine or number sine and number cosine, you kind of remember that some formulas look like that. Some formulas have something like that. X is r cosine theta and y is r sine theta. That's what we use in previous examples. So you kind of want to have that. But to have that, you would like to have r in front. What did we do to get that r? Do you remember? We multiplied by r, yeah. Multiplied by r both sides. Left-hand side and right-hand side, like so. Then it becomes r squared cosine squared -4, and I'll put in purple, r sine theta. That's what we have now. Now this r sine gives me y. So it's very beautiful. -4y. Beautiful. This gives me what? X squared. Because r cosine is x. Boom, the equation follows right away. X squared equals -4y. That's what it is. This is actually the answer, but they in the homework would like you to write down the answer as y equals blah blah blah. So solve for y. Y equals indeed blah blah blah. -1/4 x squared. So it is a parabola. Y equals ax squared plus bx plus c. It's a parabola looking like this, negative, so it looks down. It's a sad one, concave down, and shrinked by 1/4. So now we know how parabola looks like in polar. It looks horrible, which actually supports my thought, which I mentioned before. Polar equations are highly used for whatever is spherical and repetitive. Circles. We're gonna learn spherical equations in 3D. We actually will teach you how to find the cross-section of triangle and sphere and stuff like that. So pretty awesome. But they're not used for something which are not spherical. Parabolas, cubic functions, specifically lines, all of these are horrible in polar. So they are not useful for that. But they're useful for repetitive things that looks like spheres and circles. And that's why this beautiful picture that supports this idea. This is where polar coordinates are so awesome. If you take all of this to 3D, you immediately see that in 3D we're going to be using cylindrical coordinates because that's a cylinder. We're going to be using spherical coordinates because that's a sphere, and so on. So we'll be doing lots of fun things in 3D when the front and back side is added to run and rise. That's going to be awesome. Questions about any of this?